Hello all, my name is Sathyanarayanan N Aakur and I'm an assistant professor at Oklahoma State University. Today I'll be presenting our work towards active vision for action localization with reactive control and predictive learning. Visual event understanding tasks such as action localization have focused on passive scenes where the agent cannot manipulate the geometric and physical parameters of the sensors such as fixation and self-motion. This severely restricts the ability of the observer to view, understand, and respond to the events in the scene. For example, if the object of interest moves out of the field of view of the observer, a passive agent cannot reposition itself to continue to observe the action. It must wait for the actor to return within its field of view. An active vision system, on the other hand, can reorient itself by controlling the physical parameters of the camera and continue to observe the event. We make three contributions in this work. We are among the first to tackle active action localization in streaming videos without the need for extensive training or simulation environments with reward functions. We show that predictive learning can be controlled with reactive control systems to perform self-supervised active action localization. In this work, we tackle the problem of active action localization through self-supervision in real-world scenarios. Specifically, we look at action localization where the goal is to identify and localize an action of interest in a given scene. Inspired by cognitive theories of sensory motor control, the proposed framework continuously observes, predicts, and learns spatial temporal attention maps to locate the action of interest, while a reactive control model uses this to reorient itself to keep the action in its field of view. The first step in our framework is to identify an action of interest and localize it spatially. We follow prior work in cognitive science and use the idea of predictive learning for generic action localization. We use an LSTM-based predictor network that anticipates spatial temporal features at the next time step using global scene-level features extracted by a CNN. An attention mechanism is used to spatially weight relevant features that anticipates areas of interest in subsequent time steps. The final step in our active vision framework is the continual control of the embodied agent equipped with the camera. We use a reactive control formulation to adjust the camera orientation by minimizing the distance between the action location and the current camera position at any given time instance. Here, we model this into two terms. The first term refers to the action taken by the active camera to account for prediction errors and realign itself to track the action of interest. The second term, on the other hand, is used as anticipatory control to reduce the effect of the position error by choosing an action influence generated by the rate of change of the error. This allows us to effectively reposition the embodied agent to actively track an action of interest. We evaluate our approach on both simulated and real-world environments. For simulated environments, we evaluate on the task of active object tracking. We use environments simulated with Unreal Engine to track an object of interest while controlling an embodied agent. We perform competitively with more sophisticated reinforcement learning-based active object tracking frameworks that are explicitly designed and trained for this task. We find that our approach consistently has comparable recall to RL-based approach and significantly outperform generic unsupervised baseline trackers. It should be noted that reinforcement learning-based approaches take at least 20,000 iterations to match our performance, while we are not explicitly trained for this task and does not require any rewards for training. To test the framework beyond simulation, we construct a physical setup with an active camera for evaluating generic action localization. The framework is primarily evaluated with WebMind clips to demonstrate the effectiveness of generic action localization, where the primary action can be from both human and non-human actors. We see that our approach performs well, obtaining an AAE score of 9.14 and an AUC of 91.12. We observe that our approach exhibits an ability to recover from false movements and distracted actions to some extent. We present some qualitative results for both real-world and simulated environments here. In this work, we presented an active vision framework that leverages recent advances in predictive learning for active action localization. We are among the first to demonstrate the effectiveness of active vision for action localization on scenes with complex challenges such as occlusion, noise, camera motion, and generic actions. Extensive experiments on real-world and simulated benchmarks show the effectiveness of the proposed approach. Thank you. Please do come visit our poster for more details.